Magnus Bordewich from the University of Durham, who is going to speak on consistency with the balanced minimum evolution. Ooh, I was going to say algorithms, that kind of thing. Yeah. Method.
Throw it in.
Yeah, sorry.
So I guess this is already been preempted by a couple of the other talks that nicely introduced balanced minimum evolution for me. So I'll skip over some of the details of the calculation of the actual method that I would have had in there, but I'll still do a very brief introduction just so you all recall where we are. So it's a distance reconstruction method. We're assuming there is some real underlying tree with proper lengths, and we have some estimated distance matrix delta, and I'm going to call the real tree T star. So the game we're playing is we have the matrix data, and we're trying to work out what the tree is. So balanced minimum evolution developed by Desper and Gaskell, which we heard the other day, based upon the tree length estimation scheme of Pampelin. So for any topology, we can estimate branch lengths according to the scheme from the distance matrix that we have, and we're looking for the topology that gives the smallest total length. And it turns out that neighbor joining could be regarded as greedily, well, I mean, it does greedily minimize this tree length, but you could interpret that as why it's good if you wanted. The idea then is to try and find this tree that really minimizes this, rather than neighbor joining, which will greedily give you an answer. We'll try and find one which globally minimizes the tree length, and the approach is via a local topology search. So we have some tree space with a lot of topologies which we can't possibly check all of, and hiding in there is the true tree somewhere. So we use any method we like to compute a starting tree somewhere in tree space. We check locally just the similar trees, and I'll talk here about trees that are either related by one NNI move to your current tree or one SPR move to your current tree. We'll just check locally which one is the best, minimizes the tree length, and we'll move to that and then iterate the process until we find our final output topology, which we can guarantee is at least a local minima in terms of the total tree length. And obviously the question we'll get to is whether this is a global minima or not. So the two operations, I just want to raise one point about, I think we've seen them before though. So nearest neighbor interchange is normally regarded as swapping two neighbors, whereas subtree, prune and regraft, we're cutting off some tree B and moving it all the way across. Now, really, nearest neighbor interchange can be regarded as a subtree, prune and regraft, where you only jump over a single intermediate. So if we cut B off in the top one and just jumped over D, we would end up with the same topology. And likewise, subtree, prune and regraft can be regarded as a chain of K nearest neighbor interchanges, where you sequentially jump over each of the C's. And that is really how we proved some of our results, so I'll return to that. So the approach has been programmed as FastME, and it's available on the web. It's very fast. I'd like to make the point that SPR is still very fast, even though more commonly NNI is used. I think they are both available on the web. Certainly NNI is available. They're both available. I'm getting a nod back there. And we've already heard this week about extensive experimental results suggesting that you get very accurate results from this process. So the question is, can we prove anything about whether these results are good? So I spoke earlier in the year in New Zealand, where at the time the result we had was that for any starting tree, so not even assuming that you have used some intelligent method to generate your first topology, but from any starting tree, if you do a local topology search based upon SPR moves, then the BME method is consistent. And that means with perfect data, we would get to a global minimum. So we would get the correct tree if we had perfect data. So since then, we've actually boosted the analysis a little bit, and we have shown that there's a safety radius of 1/3 on this same process. And that means that with small errors, we still get to the correct tree. So the process was to, first of all, find an SPR move which, well, when we were looking for it, we decided just to reduce the Robinson-Fools distance, but actually it's a little more specific than simply reducing the Robinson-Fools distance. So we find a pair of subtrees in our current tree, B and D, which are correct in that the subtree B appears exactly correctly in the true tree as well as in the tree we're currently at. Obviously, this is a proof technique. You don't actually find these. And D likewise appears in the true tree. However, in our current tree, they are somehow separated a bit, whereas they're adjacent in the true tree. So a pair like this must exist. And then the move you get by pulling B off and sticking it on next to D fairly clearly gives you this split BD against the rest of the world, and the Robinson-Fools distance has gone down. But as I say, it's not just the Robinson-Fools distance. This is a more specific move than just reducing Robinson-Fools distance, because we're assuming B and D as individual subtrees are correct. So if we assume this is the same move, where B moves to join D, and it jumps over K intermediate trees, then with epsilon denoting the error, what we show is that the reduction in total tree length in going from T to T primed is at least this much, right? So what that says is that as long as the error, 3 times the error, is not bigger than the edge that we're trying to recover there, that we do have some positive improvement. And so this easily says that if the error is in fact smaller than 1/3 of the minimum edge length, there can't be any local optimum. There will always be a good move. So that's essentially the result. And how we prove it is by taking B across sequentially and doing some induction with the formulae for the NNI moves in the balanced minimum evolution process, which sort of expand and begin to look horrible, but then at the end, when B joins up with its friend, they will collapse, and we get the nice result. And it turns out also that we get this factor here, depending on how far you've had to move the subtree B, so that if it was just an NNI move, here we would recover at least half of that. But if it's moving a lot further, then we recover more of this edge. So LE is the true weight of the edge in the true tree, not the estimated weight. So this gives us the main result of the safety radius of a third. But we were also asked whether we could find a single move which reduces the quartet distance to the true tree. Now, the interesting thing is that before, when we found these two subtrees, B and D, which are separated in our current tree but should be together in the true tree, I just arbitrarily moved B up. And this move gives you a reduction in the RF distance and a reduction in the tree length. However, one of the two moves, either this one where we have moved B up, or the other one where we move D down, one of these two must reduce the quartet distance. But here you do need to consider both and weigh them up against each other, whereas for the tree length we could just sort of consider either one. So there's obviously, it's nice to have some sort of consistency and justification for the process, but there's plenty of questions remaining. So we already heard that safety radius of a half is the maximum that could be attained by any distance-based reconstruction method. That's Atterson result. Here we've shown that the safety radius is at least a third, but there's a little bit of a gap there, and there isn't any particular reason at the moment to believe that it should be a third. And in a sense, if you accept that neighbor joining is a greedy but therefore less good method for minimizing the parent point tree length, then improving on that with some additional search ought to only make your results better. So you would hope that this safety radius actually also ought to be a third, but we obviously don't know about that. We also heard about other forms of robustness where you maybe try and look at edge-specific safety radius or other guarantees of performance beyond something that's bounded by this smallest edge size in the true tree, which could be very small. So there's plenty to do there. And the other question is, do any of these results hold for the NNI-based topological search? So this is particularly interesting because in all the simulations that have been done, the NNI moves seem to give you as good an answer and as good empirical results as SPR. However, the approach we've used doesn't work for NNI. Neither of the two moves that reduce the quartet distance can be guaranteed to reduce the NNI distance. And the chain of NNIs that make up this, so by that I mean that the chain of NNIs that make up the SPR do not necessarily give you a monotone reduction in the tree length. So, I mean, it seems likely that there should be good results about the performance of NNI, and that it does give you a consistent method, but you would have to think of some slightly different proof technique in order to achieve that. So, thank you for your attention.
Are there any questions? I have a question just to make sure I was following at one point, which is, but maybe we'll give other people insight, and that's be valuable. The result about the method being consistent when the distances are, sorry, the working when the distances are perfect, i.e. consistency, is, I mean, it's interesting to know that a particular method of producing a tree will get the right tree in those circumstances. In fact, the distances are perfect. I mean, you can just, as it were, look at it. I mean, there is just one tree. You don't need this algorithm or well, I mean, it's as good as any other. There will be others
Yeah.
that might be easier or might be more complicated to implement, to
Yeah, so
extract the one tree. Yeah.
this is just meant to be some sort of, well, the beginnings of a theoretical justification for why methods that are observed to work quite well do work well. But we already know, actually, that neighbor joining itself has got a safety radius of a half in this sense. So if you could somehow guarantee or expect that your errors were this small or perfect, then you wouldn't be needing this. But this is, yeah, it's not of practical importance. You don't say, look, I've got guaranteed matrix with errors at most a third. I'll go and use fast ME.
I have two questions. One, does your result strongly assume a binary tree, or does it also work if you have 0 edges but don't want to regard them as 0 edges, but rather as high degrees of symmetry? Because the half result of neighbor joining strongly assumes a binary tree.
Yeah. So as it is, we've assumed a binary tree. And I mean, effectively, the result is that we need the edge lengths to be at least so much.
Yeah,
right.
But
so with the perfect data, I'm thinking probably you could take a 0 edge length or regard it. But with the robustness one, the way we've done it, I think you need binary.
So it will be 0. Yeah. So the minimal edge, if you have a tree which is not binary, then you will have to assume that there is a 0 edge there, and then you don't get relevant.
Yeah, the way we've done it at the moment, we didn't take, or we didn't deal with that.
But do you think it strongly assumes it, or maybe it can be adjusted? You can't tell right now.
Yeah, I can't tell right
now. I'm not sure I would agree with your last note. From my own experience, it seems like on simulated data, it's often the case that NNI is probably about as good as SPR. I think on real data, NNI very often gets stuck in a local optimum, and SPR can get you out of it.
So it's okay. That's probably true. There's a difficulty with real data of knowing what the correct answer is. So I mean, probably you're right that you may not get to a global minimum in tree length, but when you're comparing how good the answer seems to be, NNI seems to give you pretty good answers. That's kind of what I meant at the end. But it's interesting. Maybe I'll talk to you more about some of the cases where NNI gets stuck, see if we can find any structure in there.
Thanks very much.